Hey guys, welcome to 11.2. There we go. 11.2. It's called Independent and Dependent Events, but maybe I should have just called it Theoretical Probability. I don't know. It is what it is. And this is about the probability of how likely something is to happen. We're going to talk about sample space, and the idea is we have this ratio of the number of favorable outcomes, the number of total outcomes possible. Okay, so let's just get right into some examples because I think this is an easy lesson. Okay, and I think we can get through it quickly, which I'm sure you're all like, oh, Mr. Refrain, but we miss your voice so much. It's okay. There's whatever. So first problem: a jar contains 32 red marbles and 28 blue marbles. What is the probability that a randomly selected marble is red? Well, we're looking for red marbles. So how many red marbles are there? 32. And how many total possible combinations are there? Well, I can get red or blue marbles, so it's just 32 plus 28. So what is 32 with 32 plus 28? .55, which, I don't really like that kind of answer. So, can I click that to make it? Oh, I didn't even know about. Look, I just noticed this. Look at this button. Do you see this? Bet you guys would have liked that, huh? If you would have noticed it. If you already noticed it, well then shame on you for not telling me. But if you didn't, so 8/15. Okay. So what's my probability of getting a red marble? It's 8/15. So that's all you're doing. You're just taking the probability of the thing we're looking for divided by all possible combinations. Okay. A letter in the word restoration is randomly selected. What is the probability of selecting a vowel? How many vowels are there? 1, 2, 3, 4, 5. How many letters are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are a total of 11 letters we could pick, but 1, 2, 3, 4, 5 combinations that are vowels. 2 dice are rolled. What is the probability that the sum of the 2 dice the next roll is at least 9? Okay, so what you can do here is, so if 2 dice are rolled, what are all the possible combinations? Well, dice go 1 through 6. At least it should say a d6. Because in Dungeons and Dragons, you have different sized dice. Like right now I have in my hand a 20-sided die called a d20. And I also have 4-sided die called d4s. And 12-sided die, and 8-sided die, and 10-sided die. And there are 100-sided die for rolling a D100. Although for my D100s, I do, I have 2 10-sided die, one with tens places written on it, or not written on it, but etched in it. These are cool-looking dice. And another 1 through 10. And between the 10s and the 1s, we know what number we rolled 1 through 100, okay? But anyway, so not very clear. 2 dice, let's just assume these are d6s. 1 through 6, 1 through 6. So what are the total number of combinations? Well, please tell me that you didn't say 12, right? There are 36 combinations, right? 36 combinations, because if I do my sample space, 1, 2, 3, 4, 5, 6, and then if the first die is a 1, the second one can be 1, 2, 3, 4, 5, 6, right? And we have to do it for all, and that's just for 1. We have to do it for all of them. So it's 6 times 6, or 36. And how many of these combinations roll at least 9? Well, that's going to be, if I do every combination, none of my 1s and 6s do, right? All right, let's, how should I organize this? What if I do, because drawing the sample space for this I think would be a little prohibitive. But what if I do this? 1, 2, 3, and then 4, 5, 6. Okay, so if I roll a 1, how many different numbers will get me a total of 9? None of them. If I roll a 2, what will give me a total of 9? None of them. If I roll a 3, what will give me a total of 9? A 6. If I roll a 4, what will give me a total of 9? Both a 5 and a 6. And if I roll a 5, what will get me that? Well, a 4, a 5, and a 6. And if I roll a 6, what will get me that? 3, 4, 5, 6. Okay? So how many combinations in total get me 9 or more? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 out of 36, which is 5 out of 18. That, there's probably a better, like, more mathy way to do it, but it's fine to just write out your sample space, all possible combinations, or do something else that visually organizes you. You know, don't worry about doing it the perfect way. Think about getting it right. Okay, so that's how we calculate a simple event. Okay, that's very easy, I think. And the complement of an event is the probability of it not happening. Okay. The complement is a probability of an event. I write not happening. Or, yeah, I don't know what's right here. Oh, not happening. I didn't even see there was more. Yeah, not happening. So some of all probabilities in the sample space is 1, right? Every probability, like if I roll a 6-sided die, what's the probability of getting 1, 2, 3, 4, 5, and 6? Well, there are 6 possibilities. What's the chance of getting a 1? 1, 6. What's the chance of getting a 2? 2 or 1, 6. Oops. That's the trap. I'm dumb. What's the probability of getting a 3? 1, 6. What's the probability of getting a 4? 1, 6. Probably a 5. 1, 6. 1, 6. So all these are 1/6, right? Assuming that our die is fair. Well, what do these add to? 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 is 1. Probabilities always add up to 1 because 1 has to encompass the sum total of all probabilities. That's guaranteed, right? What's your probability of something happening? 1. That means it's always going to happen. So what's the probability of an event not happening? Well, a probability of an event not happening is 1 minus the probability of the event happening. Right? Because the combination of an event, the probability of an event happening and the probability of an event not happening has to add up to 1. Think of it like this. If I say, what's the chance that you're a sheep? Well, maybe there's a 50% chance you're a sheep. If there's a 50% chance you're a sheep, what's the chance you're not a sheep? 50%. If there's a 30% chance you're a sheep, what's the chance you're not a sheep? 70%, right? The chance that you're a sheep and the chance you're not a sheep encompass all possible options in sheepiness and have to add up to 1, right? 0.3, 0.7 adds up to 1. This little doohickey right here is called a tilde, and it means not. There are a couple ways to write not. You can say, if I want to say not E, I can do not E for not that event, but I can also do not E. That little upside down backwards L can mean E. And you can also do EC, which is my least favorite, and that means E complement, the complement of E. E's the negation of E. I personally like the tilde. I think it's just because it's what I learned first. You know, it comes in philosophy. They're more likely to use the tilde. In math, I've seen more of this. More letters. Aren't there enough letters in math as it is? So the probability it will snow tomorrow is 7/20. What's the probability that it will not snow? Well, that's just 1 minus 7/20, which is 13/20. Right? So I think that's pretty simple. I'm not going to go through any more of that. So I want to try and keep these things a little shorter than the last lecture was 50 minutes. But I think permutations and combinations deserve that time. This I don't think does. Okay. So if events are independent, then the way that we found joint probabilities is by multiplying, okay? So if the probability of A and B happening together is the probability of A times the probability of B, okay? And if, I don't want to use a formula for this. I don't think that's a good way to think about it. But for probability A and B, it's just multiplying them together. So think of it this way. If I have I have to use dice and coin flips, okay? Let's say I have, I can flip coins. And I have true, actually, you know what? Number 11 is, a die is rolled 3 times. So that's pretty convenient, okay? So a die is rolled 3 times, what's the probability of getting 1s on each of the rolls? Well, if I do 1, 2, 3, 4, 5, 6, and then from these all branch into 6, and these all branch into 6, and these all branch into 6, and then we have a third roll, right? So this branches into 6, and this branches into 6. So how many do we have? We have 6 times 6 times 6, which hopefully you've memorized, is 216. So what are the chances of getting, that's 216 combinations of rolls, okay? But of those, how many of the combinations gives 1s on each roll? Well, from my list here, which I can tell you, you can clearly tell what these numbers are, right? For the list, I've got a 1 here, and a 1 here, and a 1 up here, right? 1, 1, 1. There's only one combination of 1, 1, 1. Everything else is going to have something else, like a 1, 2, 1, or a 1, 2, 3, or something like that, or a 3, 1, 4. So there's only one combination of 1, 1, 1. So it's just 1 over 216. Okay? Now that's nice if we can run the sample space, but what if it was something like a die is rolled 3 times, what's the probability of getting all odd numbers? Well, I don't want to count every single combination in here of 3 odd numbers. That's a lot of work for Mr. Dufresne. So let's do an easier way. We can multiply each individual probability. So if I roll 1 die, what's the probability of getting a 1? It's 1/6, right? 1 out of 6 of the numbers are a 1. Well, if I roll a second die, what's the probability of getting a 1? It's 1/6. And if I roll a third die, what's the probability of getting a 1? It's 1/6. So it turns out I multiply 1/6, 1/6, 1/6. That's the probability of all of them happening together. Okay? So you can multiply individual probabilities to see what their joint probability is if they're independent. And independent just means that previous effects don't affect later. Previous outcomes don't affect later outcomes. So, for example, every time you roll a die, that's my D20. You like that? It's pretty great. Black and red. I also got a green and black one. And I got a blue and black one too, and a black and gray one. So anyway, every time I roll this die, the number that I get has nothing to do with the previous number, right? Every time I roll my D20, I just got a 3. The fact that I got a 3 on this roll has nothing to do with the fact that I got a 16 on my next roll. And I do another roll, and I got a 15. Another roll, a 3. Okay? Hey, that's actually great that I got the 3, right? Because you would think that if I got a 3 once, future rolls are less likely to be 3s. And that's not true. Each roll is completely independent, has nothing to do with the other rolls. Okay? In fact, the belief that getting many bad rolls in a row, or that each roll influences other rolls when they don't, is called the gambler's fallacy. You might have learned about it in psychology. You know? That's why people stay on slot machines. They get on the slot machine, and they pull the lever, and they lose. And they just lost, $2 or something like that. And they go, oh, well, that was a bad roll. And they do it again. Boom, bing, bing, boom, boom, bing. And they lose $2 more. And they do it like 10 more times. And every time they lose, their logic that they tell themselves is, okay, I've lost like 20 times. Now that I've gotten the bad ones out of the way, I've got some good ones coming, so I can't quit now. But that's not how it works. The machine does things randomly every single time. At least we like to believe so. A friend of mine who has a PhD in applied mathematics actually used to work for a company programming the statistical outcomes of their machines. So, you know, if it's completely random, why would you need a PhD to do the math? Is my thought. I wouldn't trust them personally. Ever. Okay. A coin is tossed and a day of the week is selected. What is the probability of getting tails then a day starting with the letter T? How many days start with the letter T? Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Okay, so 2. So how many days start with the letter T? That's 2 out of 7. And what's the probability of getting a tails? Well, you can either get heads or tails, right? So that's 1 out of 2. So we just multiply these together. 1/2 times 2/7 is 1/7. Or 2/14, you know, but I reduced it. Because a coin being tossed has absolutely nothing to do with a day of the week being selected. Okay. Let's move on. So I'll do 13, 15 maybe. A bag contains 8 red crayons, 14 purple crayons, 6 yellow crayons, and 4 green crayons. A crayon is selected, replaced, and then another is selected. Find each probability. So, the key word here is the replaced. The fact that it's being replaced means that it's independent, okay? So if I want to find a purple, what's my chance of getting, well, first of all, how many crayons do we have all together? 6 plus 14 is 20, plus 8 is 28, plus 4 is 32. So my chance of getting of anything is something out of 32. How many purps do we got? 14. So my chance of getting a purple is 14 out of 32. Then I take that purple crayon and I stick it right back in that bag. So I still have 32 on my second pull. And now I'm going to grab a yellow. 6. So it's 14 out of 32 times 6 out of 32. Which, let's see if Desmos can help us, huh? Because I don't want to do that. Times, was it 6 out of 32? Look at that. Bam! 7 out of 32. Oh, wait, that's 12. There we go. 21 out of 256. It's a lot better than doing the math myself, huh? So this is 21 out of 256. I did the right numbers, right? 14 and 6. Oh! 14, 6. Okay, good. So that's all there is to it. The rest of these are exactly the same. 2 purples, we have 14 30 halves multiplied together. 2 of them. Okay, let's talk about dependent events, which are a little more complicated, but I still don't think it's a hard concept to understand. Oh, we have to use the same concept from above. Okay, so I need to... I'll keep this in view. I won't do these down here. I'll just do like 1 or 2 of these, and then we'll be done. So, what's the chance of getting a yellow? Well, a yellow crayon is 6 out of 32. But this one says it is not replaced. If it's not replaced, then my next draw doesn't have 32 crayons, right? We pulled a yellow out. We only have 31 crayons. So the red is now going to be 8 out of 31. So that's the difference here. If we did yellow then red, if I did probability of yellow then red up here, it would be 6 out of 32 times 8 out of 32, right? Because I replaced the crayon up here in this problem. These are replaced. So once I grab the yellow out, I put the yellow back in, so there's still 32 crayons total. Down here, when I grab the yellow out, I keep it out. So now there are only 31 crayons to pull from. Okay? And this is most tricky. And it's not that tricky, but this is as tricky as it gets for these. What if I do 2 reds? Well, the first red is 8 out of 32. Right, that's my first pull. 8 out of my total of 32. And then what happens? My second pull, I'm trying to get a red. There's only 31 left. But also, there are no longer 8 red crayons. There's 7 red crayons. So my entire probability goes down by 1. There's 1 fewer red and 1 fewer crayon total. Okay, so I'd multiply this together to get my answers, which I won't bother to do. There's my answer, smiley face. You can type those in yourself. Nothing really to gain there. And I think that's it for 12.2. Okay, so have a good one, guys.